welcome Kris. So he's coming to us from Montreal as well. He's a PhD student at the Milan, postdoctoral student at the Milan, where he's working with Joshua Benjo and with Susan Holmes on humanitarian AI.
Okay. Okay, thank you. So I'm really happy to be here. It's nice to see so many people here. So I'm going to first, the first few hours, I want to focus on just the foundations of deep learning. And to be honest, I wasn't sure how I wanted to introduce it. Because on the one hand, I was thinking like a common way to introduce deep learning, maybe we can just talk about the big successes. We can talk about ImageNet, I can talk about Go, I can talk about autonomous driving. But then I thought, oh, you know, I'm not flying 20 hours to tell you things that you already know. Like, what's the point of just repeating these things without getting into any depth, right? So I didn't want to just introduce the successes that everyone already knows. On the other hand, my instinct is, okay, let me just dive into the math. But then when I thought about it again, I'm like, that misses the point too, right? Like, there's excitement about this field, and it's not because people really love to take derivatives, right? And then maybe blame it on the jet lag, but then it struck me as, deep learning is just like poetry. And what I mean by this is that it's an amazingly expressive language, right? It's a kind of a vocabulary that when you put it together in very creative ways, then it can really move people. It can like tell interesting stories, right? But then in and of itself, it's just the pieces. It's just the words, right? So I think of like knowing stochastic gradient descent is like knowing meter in poetry. You need to know it to be able to do it. You need to have the foundations. But then in the end, the thing that we celebrate is ingenuity, right? We celebrate creativity. When we see people think about how humans reason and how we pay attention to things and we learn how to translate that into programming, that's creativity, right? Defining an attention mechanism in code, that's brilliant, right? But then it's not just the math, right? So it's somehow, you need the math, but there's something a little bit more. And that's kind of my hope is, at the end, I teach you some of the basics of the form, but then you write the poetry, right? So this is my high-level goal. And here's a nice little poem I like. Okay, so what's the plan, at least for this first lecture? One of the things I hope you leave is just understand the high level, what are the goals of deep learning, right? It's a suite of techniques that have a few ideas in common across all of them, especially representation learning. So like, what is representation learning? We get into that. I want to trace out the development from logistic regression to backprop, right? So I know you already discussed logistic regression a bit, so I want you to see that there's some continuity. I don't want it to appear that all of a sudden deep learning is this magical toolbox that's totally disconnected from history. It's actually very deeply entwined with the history of machine learning. So that's actually most of this lecture. In the end, I just want to have a few tricks about how do you actually train these things, right? Because this seems to be something that like you often hear people say that deep learning is an art, and then they never tell you anything more. So I want to tell you a little bit more about like, okay, what is the actual day-to-day art of getting things to work, right? Because it's still a relatively nascent field, there's not as much that's written. And then hopefully throughout the lecture, I can communicate this last point, which is like, how do you actually, after the school is over, right, how are you going to teach yourself more about deep learning, right? And I think that there are a few tricks that are very, very helpful, right? And I'm going to try to exemplify them in my examples and in my presentation, but just kind of give a foreshadow. I think when you see a complicated new algorithm, try to reduce it to something that you understand. Try to reduce it to something that's very simple. Like study the toy examples. And then when you see a formula, like draw a picture, right? Like the equations are really there to formalize some sort of intuition people have, right? So we'll see more examples of that, but that's something I want you to keep in mind, because this is a lesson that you can, once we're gone, you can still understand a lot that way. Okay, and then ask me questions. Here's an old quote from Francis Bacon, which I think is really great. Truth emerges more readily from error than from confusion. Right? Being confused about things isn't productive for anyone. But making a guess about what you think is right and being wrong, that's a way to actually learn things. Right? But what I really mean by this is I have chocolates. So if you ask me a question, or if I ask questions and you give me an answer, you get a chocolate. So here you go. No. No, this is silly. Okay. Any questions? No. Okay. So now we get into the real work, right? So you've already seen this, right? We have a sequence of n coins. We're flipping them. Each of them has a probability pi of turning up heads, right? I guess you've already seen kind of this sort of likelihood function, right? This is pi for getting heads. Indicator yi is 1 means you got a heads. Yi being 0 means you have a tails, and the probability of having tails is 1 minus pi, right? When you take the product, that's just considering each of these events is independent. So since probabilities of independent events multiply, you can just multiply all these probabilities together, right? So this is where that formula comes from. And then since we're doing log of a product, that's the sum of the logs, right? And you're summing this kind of function. And this is the binary cross-entropy function, right? Again, now starting to think about pictures, right? What does this function actually look like? It's just this, right? This is when you have 1 heads and 1 tails, right? So the likelihood is the highest at the probability being 0.5. Right? Because you've seen one of each, you don't really have a better guess of what it can be. So you just say the maximum of these likelihoods is going to be 0.5. Right? That's all what maximum likelihood means is you write down a formula like this. It has some parameter that you don't know. In this case, it's the probability that it's going to turn up heads. And you're trying to figure out what is that probability just looking at the data. What you do is you guess, well, what if the probability is 0.8? And then you look at the likelihood. It's not that high. What about the probability being 0.1? You look here, and it's like, it's still also not that high. But then probability 0.5, then it's pretty high. So then you think, like, okay, this is my maximum likelihood estimator. All right. And then the neat thing is, now that we have a formula, we can play around with all sorts of numbers, right? So when I have, this is 3 heads and 7 tails, that means yi is 1 for 3 of them, and then the rest of them are 0, right? I just compute this formula. It ends up being like 3 times log pi plus 7 times log 1 minus pi. That's just this formula. Looks like this. And the new high point is at 0.3. Or, sorry, yeah, 3 out of 10. Right? You can play this game with all sorts of numbers. 30 heads, 30 tails. Something interesting happens, right? These are exactly the same functions, right? The only difference is that this one is scaled times 10. And it makes sense, because I took the same formula and I multiplied it by 10. So, of course, the function looks the same. It's just 10 times lower, right? So, okay, this is how the likelihood works. But now we ask a more subtle question, right? So far, I'm thinking about tossing all sorts of independent coins. They all have probability pi. Life is easy. You can just do maximum likelihood. What if the probability of turning up heads dependent on some sort of input variables, right? I mean, kind of the picture I have in mind is I'm going to color any of these dots red or purple, but then whether it's red or purple is going to depend on where it is in the scatter plot, right? So think of this as like a, in the coin flipping example, maybe it's like, does the person have a disease or not, right? And instead of thinking about every person having disease independently with the same probabilities, maybe certain factors predispose you to have that disease, right? Maybe your age, maybe where you live, maybe your family history, right? And each of these things is going to affect your probability, right? So we're basically in a situation where we're doing coin flipping, but then our coins have different probabilities, and these probabilities depend on some input data, right? So the way we notate that is we still again have pi. This is our probability, but the probability depends on input data. It depends on all these factors about you, right? And then visually you represent that by the input data you plot out in some 2D thing. So maybe this is like a age, and that's kind of distance from closest hospital or something, right? And then you see, okay, what's the chance? Like each person can be parameterized by these two numbers. You get a point, and do they have the disease or not is the color, right? So intuitively, you look at this, and then you think like, okay, I can kind of separate these two groups based on their, or like you can separate the heads or tails, the has the disease or not having the disease, just by drawing a line in this feature space, right? It doesn't have to be that simple, right? Maybe the appropriate thing to do is draw some sort of curve, right? But then the basic idea is this, right? We're going to have some probabilities. The probabilities are going to depend on characteristics of the people, right? And then somehow we're going to learn a model for separating the like highly probable cases from the very low probability cases just by looking at the input data. Okay, everything makes sense so far? Okay. So the formula is basically exactly the same, right? So all that's different is I now have a pi of x, right? So now instead of having the same probability for every single person, I have a probability that depends on each person, right? But it ends up being the exact same formula, right? All we need to do now, so like before we did maximum likelihood for pi, now we need to learn some function pi of x that explains the data well, right? So like in this example, what pi of x would look like is you would want pi of x to be really large out here, and then kind of smaller out here, right? So that you have large probability outside of this curve, and then low probability in the other side. Okay. So how are we going to do that? Kind of, the difficulty is that if you just think about pi of x, there's so many different kinds of functions you could have, right? Like I could have these kind of weird, depending on nonlinear boundaries, I could draw different probabilities. Maybe I could have like a jagged one. It's not at all obvious how you're going to search through all those possible probability functions, right? So you need to define some search space, right? So what's one kind of typical search space is, well, just think about planes. It was like the first example, right? And one way you can parameterize that is using this function. So this is called the sigmoid function, right? The notation I'll be using throughout is a sigma of theta transpose x. X is your position in this plane. Theta is the direction of the plane, right? So this is one theta, here's another theta, this is another theta. Okay, and here I'm just kind of drawing at random 10 of these sigmoid functions, right? And so the point, what we're going to have to do is learn which of these sigmoid functions best explains the data. But this is much easier than the previous task, right? In the previous task, I was considering all possible functions. This is really hard to just write down. This is very easy to write down. And the reason, like the loss, like the trade-off is, I can write this down really easily now. All it is just different directions. But the loss is that it's not as flexible. And if everything has to be a plane, right? So, but this is what we reduce it to. And now you can just plug it into the formula again, right? So where before I had pi of x, I'm now doing pi theta of x, right? So pi theta of x is a much smaller class of probability functions, right? It's just these different hyperplanes. And I'm going to figure out which of these hyperplanes has the highest likelihood under my data. Okay. Any questions so far? Remember, you got to talk about it if you do.
So why did you, again, why did we choose Sigmoid function?
Oh, because it's easy to write down. So, okay, like a more detailed answer. So you need to define some sort of like separating between, well, like you need to define some sort of plane, and then you want to parameterize probabilities like high or low depending on where you are on that plane, right? Kind of the simplest thing you might try to do is like a linear function, right? Like where the direction is the theta, and then I learn some linear plane on that. The problem of doing that is that it could be larger than 1 or smaller than 0. So it doesn't make sense as a probability, right? The next thing you think of is like, well, maybe I can get something that goes between 0 and 1, right? Like that forces it to be between 0 and 1. They're not actually that, like there are a lot of choices you could have, but this ends up being like a very convenient one. And kind of more than that, it has an interpretation in terms of probability. So yeah, it's very related to like yeah, it ends up being like kind of the right one you would do if you end up doing a Bernoulli distribution. But yeah, it's a good question. And just like just looking at the formula, if I take x to negative infinity, right, then this is like 1 plus e to the infinity, right? So that ends up going to 0. The 1 divided by infinity ends up going to 0, right? And if I go the other direction, it ends up just being 1 divided by 1, because the e to the minus x, sending that to infinity, that ends up going to 0, right? So this is something that's always going to be between 0 and 1. So that's kind of the nice thing. And do you have a preference?
Well, I get it. Secrets.
Cool. Hey, first question. The bravest man. Are you open?
Well, I get everything now.
Oh no, oh no. Yeah. Mm-hmm. Okay. So we've reduced the problem of finding kind of good probabilities that are functions of data to just finding directions in this 2D space, say, that separate the positive and the negative cases really well, right? We need to just figure out what this theta is, and once we figure out theta, we're done, right? So how do you think of this? Well, I mean, just go back to this kind of picture. Like, we just need to find the maximum of this likelihood function, right? Here it was pretty obvious geometrically. This is the top point. But then in more complicated setting, what we have to do is we need to resort to calculus, right? Because the way we're going to maximize a function is we use calculus, set the derivative to 0, and then solve for theta, right? This is the usual procedure for finding maxima, right? Now, you could try to do this, right? Here's the log likelihood function I had just written, and instead of the pi theta, I plugged in what the actual formula is the sigmoid of theta transpose x, right? It looks like this. And you can try to differentiate this with respect to theta. Now, it's doable. You can try. But then this is the sort of formula where, like, if I had put it on a calculus exam, all the students would hate me, and like I'd probably get fired. The principal would be like, "What do you think you put this kind of formula on an exam? This is crazy." It takes a while, and it's really tedious. And if you had to do this every single time you derived an algorithm, we would still be doing logistic regression, right? Like, we would not have made any progress in deep learning. So we need a smarter way of taking this derivative. And the magic is going to be coming from the chain rule, right? So it's another way of looking at that formula, which makes things very clear, right? So first things first, there's a lot going on here. In terms of the formula, I'm just looking at one of these terms of that summation. It looks like the thing on the top, right? Y log of this. There should be a sigma around the theta transpose xi. But the point is that I can write this as a sequence of operations, right? First, take my theta and then transpose it with xi. Because everywhere else, whenever I see theta, it's always transposed with xi. And then whenever I see the theta transpose xi's, just throw that into sigma. Because whenever I see theta transpose xi, it appears in a sigma. And then now once I have that sigma, I just do y log sigma plus 1 minus y log 1 minus sigma, right? And that's like a simple function of sigma, right? So I can write it as a composition, right? So what this loss function is kind of a composition of these two functions of theta transpose x. And if you want to be pedantic, theta transpose x is a function of theta, right? So this is just three functions applied to theta, right? And then chain rule, like the chain rule says that if I'm doing a derivative of a composition, well, that's just the product of the derivatives of each of the elements in that composition, right? So it reduces a really complicated derivative into three more manageable derivatives, right? So that's like the magic of the chain rule, right? So now, if the formula seemed a little bit crazy, I think there's a nice way to just visualize this as a graph. And we'll revisit this idea in a little bit more generality later. But think about the flow of computation, right? Think about what goes into this formula and then what ends up coming out, and how did we get there, right? So what goes in? Well, you needed the data point xi, and you needed theta. And the reason I'm drawing them as rectangles is because I'm thinking of xi being some vector, right? It could be just two numbers, in which case it's like the scatter plot before. But it could also be a whole bunch of attributes about this person, right? In which case it's like a long vector. And theta is also a long vector because it's like a kind of for each of those attributes, they either make you more or less likely to have the outcome, right? So each xi has its own theta, right? What's the first thing I do with them? Well, first I just pass them in through this theta transpose xi. So that's this first arrow. And the line is supposed to represent, that's a linear function of theta, right? The next arrow, I take that theta transpose xi, which is now a scalar, it's a number. When I do a dot product, it reduces these two long vectors into single numbers. So it takes these two rectangles, turns them into a square. The square I pass into some nonlinearity, which is going to be the sigmoid. That gets plugged into this square. And now I take my data point, the label, yi, this is the outcome, the heads or tails, and then I compare that with sigma via this loss function, right? This y log sigma 1 minus y log 1 minus sigma, right? And that's this function that I'd been plotting in the blue before, right? It's this kind of upside down U-shaped thing, right? So I'm just passing the original theta and xi through this kind of sequence of operations, and at the end I get this loss, right? So this is another way of viewing the flow of computation that went on in this logistic regression, right? Yeah, and we'll revisit this. This kind of the name of this sort of diagram is called a flow graph. The reason this is useful is it lets us see kind of what are the actual objects that are being stored in the computer, right? These are each of the nodes. And then the edges are what operations do I apply on those objects to get to produce the things that are in the computer, right? So I apply operations, move around things in my computer. Okay. So to see why this is going to be useful, that we need to review the chain rule a little bit, just in case as a refresher. So I don't know about you, but when I took calculus the first time and I had to memorize the chain rule, I just memorized the chain rule. Like I learned how you do it, and I didn't really ever think about like why is this important? Like what is this actually doing? And it took me like 4 years of a math degree later to realize that This has a very nice geometric intuition. And the way I think about it now is I have a composition of functions, right? So the way, like, f composed with g of x is like I apply g to x. That turns me into g of x, right? So this is g of x. I get some point in the blue, which is g of x. I evaluate a new function f at the solution g of x, right? And I get some new point, f of x, right? This is just what composition is, in 1D at least. And then derivatives, that's like what happens when you perturb things, right? Like df dx is when I change x by some tiny epsilon, how does my function change, right? So derivative in this kind of compositional sense, what it means is I'm going to change x in this first function. I'm going to change it by epsilon. And then I'm going to see how, passing it through this whole machinery, my f of g of x changes, right? So when I push x by epsilon, it changes g a little bit. So I get g of x plus epsilon. And then when I evaluate g of x plus epsilon, I get some new point on f. And like the amount that this is changing, that's the number that I care about, right? It's when I change things at the beginning of the flow, how does it change things at the end of the flow, right? That's the thing on the left. The chain rule, and this is a totally non-trivial fact, is that you can express this as the thing on the right, which is much simpler, right? The thing on the right, so what is the first one? df at g of x, right? So this is on this kind of second function, I look at the slope at g of x. And then the thing on the right, dg of x, is at g of x, I look at the slope at x. And it turns out you think about the perturbations just in this function, and you think about the perturbations just in that function. And then if you multiply those perturbations together, you get what you would have had if you had perturbed the original point in this composition, right? So think of chain rule that way. It's a way of expressing perturbations of compositions in terms of the product of perturbations of each individual function. Okay, and if we can do it for 2. Oh yeah, question? Mm-hmm. This is g of x plus epsilon, yeah?
So the epsilon should be outside the bracket.
I think so. Because, like, take the left case, it's x. If you take the difference, it's basically we are taking derivative of f, and it should be f of x, and it should be difference between f of x plus epsilon and f of x, and f of x plus epsilon would be f of x is basically g of x, and f of x plus epsilon would be g of x plus epsilon.
So I think you're thinking of like the derivative of g, right?
Derivative of f.
G is like g of x plus epsilon minus g of x, right?
G of I think I'm just thinking about the bracket. Like f of x. So for computing f of x, we are basically on the x-axis we have g of x, right? And we are computing f of x plus epsilon. We have g of x, and then close the bracket plus epsilon.
Okay. Yeah, if you want to draw it on the board, that helps. I think the confusion might be that I'm thinking about the composition, right? The moment we've been waiting for, you can use chain rule to get the derivative for logistic regression really, really easily, right? What looked like kind of a nightmare to do by hand at first, right? What would you have to do? You'd first do the logs, and then you had to figure out what to do with the x bit, and then you'd have to figure out the x's inside, right? So that's crazy. But instead, just define these 3 functions, right? There's the loss evaluated on sigma. There's sigma evaluated on some argument z. And then you have this linear thing. You can compute the derivatives. So this is a nice exercise for yourself if you want to try later. The derivatives of all these functions are very easy to compute, right? And then you just multiply them, right? So this is the derivative of the first thing on the outside, the derivative of the next one on the intermediate, the derivative of the last thing is just xi, right? And now I just cross-multiply, I get this expression, everything cancels, I'm left with yi minus pi, all of that times xi, right? This is the gradient for a single term in logistic regression. So you might have already seen this in the previous section, right? But now we have a kind of a simple derivation of that fact. And it has a very simple interpretation too, right? So this is, again, every time you see a formula, plug in numbers, right? So what happens if my prediction is very good? What happens when pi of theta, let's say yi is actually 1, and pi of theta is like 0.95, then my gradient is really small, right? That means you don't really need to change theta very much to get to the maximum, right? But then what if it's really big? What if yi is like 1, but then pi of theta thinks it's like 0.01? Then this gradient term is very large, right? Which means if I'm doing some sort of gradient update, right, like gradient ascent on my likelihood, I would need to move that theta by a lot. Because you're very off, right? It makes sense. If you're very incorrect on that example, it's telling you you need to change theta by a lot, right? So that's a kind of simple interpretation for this gradient in the logistic regression term. Okay, so that's logistic regression. And now we get to the more interesting questions. Also, when I Googled this image, this is a very classical problem in kind of multitasking learning, or we'll talk about this later, this kind of, how do you classify a yak, right? Image classification, all our examples are horses and cars and airplanes. Like, what is my classifier supposed to do when it sees something that looks totally different, right? That's like the canonical multitask learning setup, right? And then I Googled it, and then I heard like they're from Nepal. It's like, oh man, what if anyone can tell me where I can find one of these creatures, I'd be very grateful. But then the point, right? So like image classifiers, right? They take pixels and they're supposed to figure out what's inside of the image, right? You have this yi that's an indicator over all these different classes. One of my classes in this case is going to be, there's a yak here, right? Now the issue, right? When I had logistic regression, each of my xi's have to be some sort of meaningful feature, right? Because like the thetas, all they do is they say like, oh, when you have this attribute, I increase the probability. When I don't have that attribute, I decrease the probability, right? Each of those attributes, the only way an attribute enters into the probability is through some sort of like a one at a time input data, does it increase or decrease? That's what this like theta transpose x means, right? It's just a linear function of theta, right? And that's not very useful when you work with pixels, right? When I increase the like red value for that pixel, how does that change my prediction? That's not meaningful at all, right? What would be great is if someone had gone into all the images and written down, maybe not the class label, but maybe some like generic annotation information, right? Like if someone had said like, oh, there are rivers here, or sorry, there's a mountain here, there's no river, some animal, and it's not scary, then I would say like, oh, okay, maybe it's a yak, right? Like from the attributes themselves, I can do some sort of linear combination of those attributes, and I get some sort of meaningful prediction. But just working on the raw pixels, that doesn't work, right? But that's all we have, right? We don't have someone who's gone in and labeled everything, right? And the same thing is true with text, right? You have text data. It would be great if it knew that Google was an organization and that 2014 and -98 are years, but you don't have that, right? Like we don't have there's too much data to go in and actually annotate everything, right? So it would be nice if we could learn these sort of representations, right? And that's really, at the end of the day, the main goal of deep learning, right? You want to learn from a raw image what are some useful high-level concepts associated with that image, or from a text passage, what are the high-level concepts or like terms, semantic units of this text, so that any downstream tasks, it doesn't really matter what the downstream task is, you can use those more meaningful features. Right? That is, like, no matter what people talk about, human level performance of whatever, like the real goal of deep learning is to learn like representations in some sort of unsupervised way, right? Maybe you use a supervision to fine-tune it later, but it should learn from just images. What are the semantic components? How does this look like in practice, right? So it's kind of I don't know if I have the link for this paper. This is by Zeiler and Fergus. It's one of the kind of classical texts in deep learning. What they do is they take each of these feature or like learned weights, and they look at parts of the image that are like highly activating. Like we'll get into more detail about what all this means. But the point is like, okay, this bottom middle filter is like this kind of homogeneous green color. When I look at the images that are or like parts of images that are very kind of highly correlated with this learned feature, I get all these kind of homogeneous green things, right? How about now like the bottom left, right? I have these kind of diagonal stripes, right? It's learning some sort of edge detection. And when I look at representative images from the raw data set of patches, which kind of have high correlation with these learned feature elements, it's a lot of these kind of diagonal-looking pieces, right? So these aren't high-level features. These aren't kind of the meaningful features in the way of like having, there are mountains in this image, kind of high-level features, but there's something, right? It tells us that we have diagonal stripes, we have this color. It's some sort of kind of like first order up meaningful feature associated with the raw image, right? That's layer 1. What happens when you do layer 2 is you get things that are slightly more complicated, right? So instead of just edges and colors, you start noticing things like, circles, right? Maybe these are like all the bands, like kind of circular patterns that are going kind of down to the left, right? So it's learned slightly more sophisticated features automatically. And the point is you can do this for several layers. And kind of 4 layers in, it's not even that many layers, right? 4 layers in, it's already starting to learn things like here are the faces of dogs, right? Here are these kind of spiral-ish patterns, right? So that's kind of, this is what we eventually want to arrive at, right? But it's not at all obvious how we're going to do this, right? And it's not just images, right? Like the images is very easy to look at, the compositionality, but then you can do this in text too, right? And kind of what is this paper doing is also looking at like particular neurons, right? And seeing what they activate. And it's finding like, oh, this one neuron is finding, is it at the beginning or the end of a sentence, right? So like when it's kind of, it like changes the value from beginning to end of the sentence. Kind of this neuron learns, what is it? When it's inside of a quote, right? Whenever it's inside of a quote, it just lights up, right? Here is kind of the depth in code. So if you have like a nested for loop, it will get larger and larger values when you're deeper in the for loop, right? What's amazing about this is that like this is the sort of thing you might have had to tell a person to do by hand, right? You might have asked like, okay, go through this code and like annotate the depth of the loop, or like tell me when I'm inside of a quote or not, right? But then it's able to learn kind of those sort of feature annotations like relatively painlessly, right? So that's what we want. So we're going to get there. Now we begin like, okay, it would be cool if we could do that. How are we actually going to do that, right? So the first thought you might have is like, okay, let's extend logistic regression, right? Logistic regression was only learning these planes, right? Maybe if I mix them together or like stack them on top of each other, I can learn more complicated functions, right? Maybe like 2 planes that intersect with each other is more meaningful than just a single plane, right? So I'm drawing a new flow diagram. And yeah, let's see how we can make sense of this. The top left, this is xi still. This is my input data. But now instead of having a single theta, I have 2 of these w's, right? And the point is these 2 w's correspond to like 2 different logistic regressions, right? the first W gives me that kind of one increasing logistic regression, sigmoid. The second one gives me this kind of like decreasing thing, right? And that just comes from like different values of W, right? Or like different directions in my plane for the Ws, right? So I can just learn two different logistic regressions. We know how to do that because we can do one. That's fine. But the clever thing you're going to do now is you have these different kind of outputs from the logistic regressions, and you're going to combine them. And the way you're going to combine them is you're just going to do some sort of linear mixing of them. And the point is, like, if I add that function with this function, I can get something that increases up to a point and then decreases again. Right? Because I mixed together some increasing thing and then some decreasing thing, so I get something with a bump. Right? So it's not a crazy idea. And like, if I increase the W, like the first coordinate, then it will be kind of increasing a lot and then maybe decreasing very little. If I make this coordinate really small and this coordinate really big, it increases a little bit and then decreases a lot. Right? So it's just, how do I mix together these two intermediate sigmoid functions? So, I mean, you can try it. It's a nice idea. A discussion question for all of you. I'll give maybe a minute or two. You can talk to your neighbors about it. One of these functions cannot be represented by this kind of function approximation, right? So think of like, what can be represented by this cell, right? And at least if I was not jet lagged enough, or like this should be fine. Like one of these is not correct, or like you can't approximate. So talk about this for a minute with each other. And then also think about any other functions that you can't approximate, and then get back to me, and I will ask you your response.
I think the first one and the second one.
Talk with each other first.
Question you त्यो दुईटा त्यो इक्वेसन मिलेर थप्नु Excuse me, can you repeat that question again?
Yeah, so it's kind of these four, one of them can't be approximated as a mixture of these two logistics. So which one is it? Okay, I think people have more or less figured out their answers. Okay, so, or does anyone want more time?
More
Okay,
time.
okay,
Yeah.
give us a
Just
little bit more time.
2 minutes, I think.
Yeah. Okay, yeah, anyone volunteer an answer?
Yes. I think the answer is the second one.
So which, what do
The
you?
second, the one on the top right. Yeah.
Okay,
Yes.
and why?
Because you cannot get that result from a combination of two separate functions from the previous slide, right?
Well, I don't know if that's a proof. Any more detail? Like, what is it about this that's so different?
Just like three, you need at least three
Yeah.
those logistic functions to create that.
Yeah, that's it. Like, it has 3 turns, right? And the others only have 2. So to get that kind of third move, it needs to include a third logistic function. And that's all. Any other thoughts of like other functions that could not be learned besides just like increasing the number of bumps? Any thoughts? Okay. I mean, basically, kind of, if you think about like even just, oh yeah, you have a suggestion?
The non-convex one?
Or so these, like, I mean, some of these are already non-convex, right? So you can learn non-convex functions this way, right? But then, I guess there, if you want to get different kinds of slopes, that's going to be really hard because like logistic forces you to have a certain kind of slope, right? If you want to have any kind of like hard crosses, right, that's going to be really hard to get because this is always some very smooth thing, right? So like these are the sort of functions that we might want to actually learn, but which just mixing a couple of logistic functions is not going to cut it, right? Okay, but this gives us some motivation for thinking about what comes next, right? So we've thought about mixing two, and we found that it's more expressive, but it's not as expressive as we'd want it to be, potentially. So what do we do? Kind of the first thing you might try is like, okay, let's take k of these logistic functions for some large number k. And now let's try mixing them all up with each other. And now we're going to be able to get kind of k bumps, right? Which potentially a lot more, right? That's this kind of more complicated function at the end when you mix them all together, right? So yeah, and now this is just kind of like notationally, this gets a little bit more complicated to draw, right? Like I need to have k of these w's, and then I have a last one that's figuring out the weights for each of those k functions. Notationally, what I do is I just combine all those k of them into one big matrix. So each row of this is one of those small vectors. And now, yeah, it's just like a simple diagram, right? I basically, the w's I stacked into a matrix, all the green individual functions I stack into one big vector. I'm calling that vector h1. Yeah, and then this is kind of much more convenient to write. This is called the multi-layer perceptron, actually, if you look up in the literature, right? This is called the hidden layer in the multi-layer perceptron, and you're just kind of combining this hidden representation. And this already gets us some notion of kind of representation learning, right? Because this intermediate H1 might learn to kind of activate on certain parts of the domain and disappear on other parts, right? It's probably going to be more like the edge detector thing that I show at the beginning. It's not going to learn these higher level semantics, but it's already introducing some kind of intermediate level of representation between the response that I want and my original xi. So like using this h1 might start to serve as some sort of annotation. Now, okay. Do I have the same slide? Yeah, same thing. Okay. The basic idea of deep learning now is I can try to learn representations by composing this many times, right? So like I already gained a lot by mixing the k logistic regressions at one stage, but what if I took the output of that, and these are now much more complicated functions, and then I mixed them k different times, right? And I'm going to keep on doing this mixing thing many times over, right? So all that changes between this diagram is, oh no, sorry, this is different. All I did here is I added the yi, so that you can see that there's a loss function between my learned representation and then the thing I'm trying to fit. And now, yeah, okay, I compose it k times. I get these k intermediate representations. Kind of each of these rectangles are weights that I need to learn. How do I, like, what are the underlying parameters of my kind of kth order logistic regression thing, right? So, yeah, I mean, that's the basic idea of deep learning. And maybe another thing that I should make sure it's clear is like, this is basically like the flow diagram I had showed for logistic regression, right? It's like I have all sorts of input. They're things that go into a computer. It's like either the W matrices or these kind of H vectors. Each edge is some sort of operation I do on that, right? So like kind of this two edges here is like the sigmoid function, right? And I'm doing the sigmoid on each element of that output vector. Right, so it's just I want to make sure that the representation for deep learning doesn't seem totally different from the representations for logistic regression. It's actually the same underlying math. It's the same kind of, you can even use the same notation. It's just what is kind of crucial here is that I'm learning these intermediate representations, and that's not something that you have in logistic regression. Okay, yeah, so just so that you are familiar with the parlance of deep learning, I've been talking about this sigmoid function all along, and kind of to your point, like why the sigmoid? And the answer is really you could use anything. So this is just from Wikipedia. If you search for activation function, you get all these different kinds of activation functions, right? Kind of people these days use the Relu a lot. It's just kind of up to 0, it's 0, and then afterwards it's the identity function. The reason for that is a little bit more subtle, but then, yeah, the idea is like you are actually free to use all these different kinds of activations, and all that happens at the end is where before I was kind of mixing the logistics, now I'm just kind of mixing Relus together, right? Or like mixing any of these underlying activation functions, so that I just learn that underlying function k times and mix them together, right? So you approximate different kinds of functions when you do it that way. Okay. Any questions about kind of the setup for deep learning? Or like this notation?
So, why is actually Relu activation function much better than sigmoid, and how is leaky Relu function better than Relu? I need to know a little more intuitive about that.
Okay. Yeah, I hear. So the question is kind of why Relu rather than sigmoid, and then the second question is why leaky Relu rather than Relu, right? So kind of the couple answers to this. For Relu rather than sigmoid, the kind of maybe first answer is like computationally, it's very easy to do Relu comparatively, right? You just clamp down things below 0 to 0, right? You don't actually have to even multiply any new things, right? Kind of a second answer is that it increases to infinity, while sigmoid stops at 1, right? So like the gradient is still there even for very large values, whereas in sigmoid, kind of the gradient ends up just kind of flattening out. A kind of third answer, and I think it's maybe the more compelling one, is that it was not at all obvious which activation you should use ahead of time, right? And the only reason people kind of stumbled on Relus and thinking that they're actually more useful is they did a lot of careful experimentation, right? So people actually studied what are the kinds of activations you're getting and what are the kinds of gradients you are getting at the different iterations of training for some common types of models. And then kind of systematically finding that, okay, I'm noticing better gradient propagation here, and I'm noticing faster training convergence for this class of activation functions. But it was never apparent ahead of time, right? It had to be people laid out a hypothesis like maybe one of these activations is better. They ran a suite of experiments, and they actually like did that kind of analysis. In a way, it feels very quaint compared to the way deep learning is working right now. It feels like, that paper, it's one of Joshua's papers from, I think, like 2013, 2014, about Relu. It doesn't talk about any kind of benchmark leaderboard performance or anything. It's just, here's what people do in practice, and here are the different kinds of activations that people often think about. Let's just study it very carefully and understand it. And I think it's very, that's important kind of work that sometimes gets lost by the sidelines every time you see the new kind of leaderboard score. But yeah, I think that's a long answer to the question. Well, and then leaky Relu versus just Relu. I mean, I think the main point is that if there are neurons that are like never activating, that's not very useful either. It's like it's never going to update that weight, right? So you want to be able to have some updates, even if it's sort of like epsilon greedy if you're doing online learning, right? It's like some of the time, even if it's not optimal, you want to have some update just to maybe change the dynamics. Yeah. Okay. So now I'm going to talk. I told you the architecture and kind of what are the mathematical operations. I showed you maximum likelihood for logistic regression, like that's how we would fit the logistic regression. But now we need to talk about how are we going to optimize these deep learning models. And I know Ajad mentioned stochastic gradient descent, right? So this is kind of SGD or variants of SGD are typically how people fit deep learning models. And what does that do geometrically? Think of it as, here's just 2D, right? But then imagine it in very high dimensions. Each of these parameters, each of these kind of W's that are defining the different hyperplanes, and I'm mixing together all these different hyperplanes now, but each of these W's, I need to figure out the configuration of them, which does a really good job of separating my positive and negative classes, say, right? And you need some way of searching through all those W's, right? Since you can't kind of differentiate it and set it to 0, you just try to update the weights in a direction that seems better each step, right? So the way you would kind of draw that is I have some sort of loss function over my W's. So each configuration of W gets a different error rate on my output, right? So you draw that loss function over my configurations of W. I'm trying to get to the low point there. Kind of early on, I had this kind of naive function, which doesn't fit the data well. And then I kind of iteratively update by moving in a direction that decreases this loss. And each time, like remember, each configuration of W corresponds to some function, right? The ideal configuration is this function, and it's at the minimum of the loss. You don't know that yet, so you start off with this function. And then each step, I kind of modify my function a little bit, right? And I modify it in a way that brings me closer to the true function, which has low loss, right? So this is kind of the geometrical intuition. The reality is it gets much more complicated when you're in high dimensions, but let's just build some intuition. Okay. So we need to estimate the parameters, these WKs. Now this seems really complicated. And for the same reason that the logistic regression, when you do the derivative in logistic regression, that also seemed complicated, right? And like, what is the source of that complexity? The source is that when you change the W early on, the effect is going to propagate all the way down the network, right? And you need to keep track of how those effects are going to propagate, right? So, right, like here, let's say I change W1, right? That changes my representation at H1. And that change in the representation at H1 changes my representations at H2 and on until it gets to my final thing, which I make my decision based off of. But you need to keep track of that, right? So just thinking about that derivative is complicated. But then again, we just learned about the chain rule, right? So this is the key. We're going to use the chain rule to escape the complexity of keeping track of all that propagation by instead of thinking about the propagation one layer at a time. So I'm really excited about the chain rule. I have so many slides about the chain rule. Here's another way of thinking about the chain rule. Here, like before, we were only thinking about basically univariate things, right? Like 1D to 1D, and then you compose it many times. Now I need to have some sort of chain rule for multivariate things, right? So how do you think about chain rule for multivariate things? I have X, my input, Y is some vector valued output, H is some intermediate thing. I'm going to pass it through two functions. And you want to think about how does changing a little bit one of the coordinates of X affect the output coordinate for one of the Ys, right? So that's the kind of, so like before we were thinking about the changing on the x-axis for one of the functions, how does it change the y-axis for the other function? Now I'm kind of changing one coordinate of the input dimension for that function, and then I'm changing one coordinate of the output, right? So just notationally, how would we represent that? Think of this new matrix D of the composition, F and G. The number of rows is the number of output dimensions of Y. The number of columns is the number of input dimensions of X. And what is the ijth element of this matrix? So the top left corner, that would be like the first output. How does the first output change when I change the first input by a little bit? Right? And then kind of every element of this matrix is like, if I go to the next cell, so that's the second input affecting the first output, right? So like if I change the second input on X, how does that change the first output on Y? And I just combine into this big matrix all the different kinds of changes on the input versus all the different kinds of changes on the output. And I'm going to put this in a big matrix. And I call that D of F composed with G. Right? It's really, if you, this is a multivariable calculus class, you would just write down the matrix of partial derivatives for each of the output versus each of the input. But I find this representation easier. And the chain rule in this case, it ends up being, again, the derivative of this composition is the product of the derivatives of the intermediate steps. But here, the product is a matrix product, right? So, OK, what are df, h, and dg of x? So h is what I'm calling the intermediate representation, right? So dfh, what that is for each of the different h's, when I change that h, how does it change each of the possible y's? Right? And I collect that into this matrix. So here is all the possible y coordinates. Here are all the possible input h coordinates. And as I change kind of this first element of h, how does it change all the possible y's? If I change the next coordinate of h, how does it change all the possible y's? And I can kind of collect the derivatives for this operation. And in the same way, I can collect the derivatives for that operation and put it in this dg. And kind of magically, the dimensions match up exactly, right? From whatever the earliest input to the final output is like, here is the earliest input, intermediate step, h dimension, and then output dimension. So like it all works. And this turns out to be like, this is a correct expression for the derivative of the composition. And this is, again, not at all obvious, that you can just multiply the derivatives of the intermediate functions and get the derivative for the composition. But it's true. Yeah, and that's kind of, this is important. And now, so kind of, I'd drawn this kind of flow graph idea before, and kind of one of the reasons this is really important is that kind of, I'm making very explicit how each of basically here, I'm showing like each edge is a function, applying it to something in my computer, like x or h, doesn't matter. Flow diagrams, I can basically extend that simple diagram into very complicated computations, but at each step, you have a very explicit formula for that transformation, right? So basically, my point is, I had a chain rule for a single chain, right? What if I have a complicated graph of operations? You want to have a chain rule for this complicated graph of operations, right? So how do I do that, right? It turns out there's a very simple formula, or okay, sort of simpler formula, and like how do you read this now? Okay, so let me step back. Here is some input data. I do this sort of transformation to get hk. I do a different transformation to get this other h. Kind of at the end, I get this kind of data point. Maybe I also produce this as like some intermediate output. And what I want to be able to do is I want to be able to take this output, say, and think about how does changing one of these coordinates affect my response here? Or how does change something out here affect here? Right? So I need to think about how the change is going to propagate not just through a single path, but maybe through all the paths, right? So this is the basic problem. I want to figure out the derivative of some intermediate thing or like final output thing with respect to some input or like intermediate thing. And then the changes are going to propagate through this graph, right? And I need to keep track of that propagation. And the formula that you end up getting is for one of these intermediate nodes, so this is the output node that I'm trying to think about how it's changing when I change this input guy, right? So basically think of this as like a subgraph of that really complicated graph that I got, where I'm trying to get df with respect to dx, right? The formula tells you is that first, compute for each of the children nodes for that kind of thing which you're perturbing, try to learn what happens when I perturb that input thing with all of its children, right? So when I change this node, how does it change each of the children nodes? So think about that very local perturbation, which should be easy to calculate, right? Because it's just a single operation. You don't need to keep track of any kind of propagation across the full graph. You just need to think about the perturbation at that one edge, which is easy. And then it turns out, like, multiply that by what happens when you perturb that like new child node with respect to the output thing, which is it's basically analogous to the previous one, right? So it's like recursion, right? When you can write down an operation that you care about in terms of like a simple thing plus kind of the thing that you started with but slightly smaller, that's like a recursive argument, right? So I'm expressing my original, like say, this input or this output with respect to h. I'm expressing that as, well, think about first these edges, and then think about whatever follows this child to get to the output, plop that into its own df. In this case, it's only one edge, so it's not that complicated. But you can imagine there could be many intermediate edges, and you just choose to ignore it for now and put it into some new matrix. And that's what this formula is, right? J, these are the children nodes. So dfi of hj, that's like what we started with, except instead of differentiating it with respect to the original input, I differentiate it with respect to each of these children nodes. So it's like the big kind of red subgraph circles. And then dhj versus dhi, this is like the child node with respect to each of this immediate input previous parent node, which is like some simple immediate operation. Again, these are all matrices, because I'm thinking about these are vectors that are affecting vectors. But then I can just do that matrix multiplication, and I sum over all the children. And that's a good expression for this complicated propagation of changes, right? Okay, so it's a little bit of an involved explanation, but I think it's a very useful generalization of chain rule. And it's actually, if you step back, it's not anything different from what we've already done. And kind of the intuition I recommend is think about, this is like a very simple graph, but it's representative of kind of what we had before, where we don't just have like a direct chain connecting everything, right? So what I've done here is I took my original single h, and I separated it into two h's, where I have like two different functions leading to these different h's, right? But it's like a smaller dimension of the previous thing, right? And then I combine them both back through some other operations to get y. Now, the intuition is that kind of before, when I did the chain rule, I decomposed this kind of large input to output two-step thing into a product of the intermediate steps, right? So it's basically, I think about, this is the first step, that's like the first matrix, and then the second step is like the second matrix, right? But now, since I've split this intermediate thing into two colors, I can split my original matrices into the two colors as well, right? So basically, here, like in this first operation, I split the output, right? I took my single x into two different colors for the output. So basically, I take the same input, the same input, and I split it into two different outputs, right? So that's like the two colors for H1 and H2, right? And then in the same way, like here I had a single input, now I have two different inputs for this function. So it's like here, I had one input, and now I'm turning it into two different inputs, right? So this is just like a way of rewriting that original chain rule matrix multiplication in a way that kind of accounts for this conceptual difference between my intermediate h's, right? But it turns out, if you write the matrix multiplication of this kind of wider thing, you can write it as a sum over the smaller matrix multiplications of the different pieces, the red piece and then the green piece separately. Right? This is just like a property of matrix multiplication, right? And then this is like thinking about the children nodes, right? So like before, in this formula, I sum over the immediate derivatives for the children, and then from the children up to the final node that I care about. That's exactly what this is doing, right? I'm summing over these two kind of H1 and H2 children and thinking about the subsequent changes, right? So that's what this matrix multiplication lets you do, right? So this ends up being a proof of the more complicated formula if you think about it instead of just splitting it into two pieces, splitting it into some arbitrary number of pieces. You just like reorganize the way you do the matrix multiplication, and then you get that sum over all the children formula. Yeah. This is, I don't know. I like to see, like when you see a formula like this, it's nice to know a little bit of where it comes from, right? Instead of just accepting it, right? So now this is at least like the kind of geometrical argument you would make in a very simple case. Like this is obviously not as complicated as the full graph, but then it helps you build intuition for what might be happening in the full graph. And actually, this argument would generalize. Okay, so this is like the punchline, right? So if you like totally missed everything I've been talking about in the last 10 minutes, you're okay. Because what we need to be able to do is think about the derivative of the loss with respect to each of those W matrices, right? So this, you write it down as some big graph, potentially, and then we just want to find some simple way of getting the updates for all those W's, right? So think about this large graph. Let's say I want the derivatives with respect to all those three kind of inputs, right? So I want to think, how does changing this input change this output thing? How does changing this input change this output thing? Well, this formula gives me a suggestion, right? What the formula tells me is, well, do it recursively, right? If you can express the full derivative with respect to the input in terms of like the children and then everything that follows, just break it down in that way, right? So what you do, the first step, I take my output node and I think of its immediate children, right? Or sorry, this is like the immediate predecessors, right? And then I can get those derivatives very easily because it's just a single function, right? I'm not having to propagate through many different layers yet, right? So I first calculate that. But then I remember, like, okay, well, in my formula, I also need, like, eventually I'm going to need the derivative with respect to each of these intermediate things with the output, right? Because, like, the way I'm kind of backtracking all the way through, right, like, yeah, like, at least I now have a way of computing these derivatives, but now that I know this derivative, I can figure out the derivatives for each of its previous things, right? Because I take whatever this derivative is and I just multiply it by whatever is on that edge, right? So like, since I now know that, that's like, I now know the dFi I just multiply it by my single new edge, right? So I can get everything from before. And then it just flows backwards, right? So I get kind of all the predecessor nodes for this one. Now that I know this full derivative, I can figure out each of these derivatives just by multiplying it by the edge, right? So just you propagate it backwards. You start like at the very end where things are very simple. I think about all its predecessors, and then that helps me go from something very simple, and then I iteratively build it up into something complicated. So that's the whole point of introducing that formula in the first place, is that I can write down my derivative computation in this kind of iterative, like each step is very simple, but at the end you get something that was complicated, right? So this is the way that you organize gradient computation in general computation graphs. And why is this useful? It's because we can write deep learning as a computation graph, right? That's like, if you think about, Theano or PyTorch or TensorFlow, any of these things, right? They don't do derivatives by hand, right? Like the way they actually do the computation under the hood is they build a graph saying this is all the values that I need to store, and then I need to figure out a way of getting gradients with respect to each of those things that I need to update. And it does exactly this operation. It builds this large graph. It thinks about first the derivatives with respect to the immediate input to the loss, and then I just build it backwards. Like what affected the thing that I just updated, and then now I can get all the gradients, right? And that's, in this picture, just makes it very direct, right? So this is like the kth layer of a network. What goes into the kth layer? Well, I have my previous representation, the hk-1, and then I also have this weight term and say a bias term for the kth layer. My first step of my my first step of my computation graph is I multiply these together. Next step, I add in the bias. The last step, I apply my nonlinearity. It's just like 3 very simple operations, each of which you can figure out the derivatives very straightforwardly. And then you just stack these really deeply. And then if I need to get the derivative with respect to WK, well, that's not so bad, right? I start off from the very bottom, and I build up, I just multiply my derivatives all the way, I march up my graph until I get to WK. And that's how I figure out my derivative with respect to WK. And that's what I plug into my stochastic gradient descent. Okay? Now, I think there's a deeper lesson here, besides just how do we learn deep learning models, right? The deeper lesson somehow is that when I needed to do this gradient computation, I only needed to look at the immediate descendants and the immediate kind of edges going in and out from a node, right? I didn't need any of the rest of the graph, right? Imagine a world where if I changed my computation graph a little bit, it affected the gradients everywhere else in a way that wasn't just multiply things together, right? If that had happened, then I wouldn't be able to define a new module in a neural network and have it integrate into the rest of the network very easily, right? Because I would have needed to define a whole new update mechanism, and it would have been a lot more complicated than just, it wouldn't have been isolated, right? The point is that, when I'm able to do the gradient computation, input to output for this single subgraph, I can plop that into whatever subgraph I want, and now compute gradient computations for that larger graph, right? So it's modular, right? That's the main idea. And I can define whatever new layers I want, and I can put that into my deep learning model, right? And then this lets people, this is amazingly liberating, right? You can come up, not only just come up with all different sorts of layers, but you can kind of add them to existing architectures and train them very easily. And I think it's very useful to contrast this with previous generations of machine learning algorithms, right? Kind of in statistics, especially Bayesian statistics, right? You want to learn how to fit a model. You derive a set of updates for that model. And then someone comes up with a new idea I think you should do this step slightly differently. Well, you have to derive all the updates from scratch. There's no way around that in kind of traditional machine learning methods. But then here, what you can do is I can just add that into my into my big computational graph, and I can optimize that all at once. And I have no additional work necessary. I can just use the same computational graph gradient computation that I've been doing all along, and I can use your proposal, and it's very easy for the community to interact, right? So I think that's actually one of the key advantages in deep learning, is really this ability for the community to kind of propose small changes, and then without having to worry about how all these other layers work, being able to experiment with their new ideas. Yeah. Okay. Do we want to take a break or something, or are we good? This is my last section for this.
Maybe you want to finish this. How long is this?
This is relatively fast, I think. Yeah. Okay. So far, I've told you how to define deep learning models. I've told you how you can fit them in theory. But then I haven't actually told you how you're going to do this in real world. And kind of the kind of the mythos of deep learning says that it's very hard to train a neural network, right? It kind of, if you trusted everyone what they're talking about training deep learning models, you might start believing like, okay, you like define your architecture in whatever framework, you like make up parameters for your optimization, you pray to the random number generator, and you hope it beats the leaderboard. And this is not how I want you to think about it. Like, this is how it's taught sometimes, but that is not how you should, that is not science, right? We need to have some way of organizing our search, right? Like, you shouldn't have to pray to get a good deep learning model, right? But let's step back. Okay, why is it complicated to fit a deep learning model? A few reasons for this, but maybe the most important is that there are a lot of hyperparameters, right? And the actual learning is going to be sensitive. Like, there might be everything else in the model was the same, but then one person trained with one version of the learning rate, another person trained with another version of the learning rate. One person's model got state of the art, the other person's model doesn't even train, right? So like that's problematic, right? In a way, it speaks to the youth of this field that this sort of thing is acceptable, right? In other fields, if you had that sort of sensitivity to parameters, this is a very bad sign, right? But then I think eventually consensus will emerge, and then people will kind of build up a little bit more practice. But at this moment, it's still relatively an art. Okay, enough lecturing. What are the actual hyperparameters? First, and probably the most important, are the sequence of learning rates, right? So every step of gradient descent, you move by a certain length, right? And this is a length that usually decreases as you get to the end of training. And you need to figure out how is it going to go from like very large steps to really small steps, and maybe that initial large step should it have been larger or should it have been smaller? This is something you need to choose. So the number of layers, like depth and width, right? These are important things. Regularization. So I haven't really talked about this, but in your loss function, you might not use the kind of straightforward maximum likelihood loss. You might add some sort of like L2 or L1. This is like basically encourage the parameters of your model to be a little bit smaller, but there are like subtle ways that you might want the parameters of the model to be smaller, and that has like kind of a bias variance trade-off effect, right? If you want the parameters to be smaller, you will have less variance in your model. And so this is something you might choose or choose not to add, right? So that's another hyperparameter. Activation functions and also preprocessing, right? So I'm lumping all these hyperparameters together, but they're kind of qualitatively very different if you think about it, right? Like some of these hyperparameters are like continuous values. Some of them are kind of ordinal for like different layers. Some of them are kind of these binary, do I do it or do I not do it, right? And it can be tricky to keep track of all these different kinds of hyperparameters. But you need to somehow specify this, right? And you need to have some sort of organized way of searching through these choices. Because in the end, once you have a final model, you're not allowed to go and fiddle with the hyperparameters anymore. You need to live with that model in the real world with those parameters, right? So it's like you can't have a human setting them all the time. Okay, what are the most common kinds of strategies? So the first, this is maybe the simplest idea you might try. It's called multi-resolution search, formally, but like in practice, all it means is if you're trying to find a good configuration of hyperparameters, first be very generous, like try a very wide range, and then the ones that seem a little bit more promising, kind of drill down on those, right? So maybe I draw a picture for this actually. So like, if at the beginning I had these kind of, Okay, yeah. So yeah, I'll try it darker. So let's say I have these kind of 4 choices for my hyperparameter. I notice my errors looking a little bit like this. So what you might do is, like, this is an initial very broad sweep. What you would do is, oh, this one looks more promising. in my next batch of experiments, I'm going to run kind of a whole bunch that are around here, because maybe like it decreased like that, right? So the basic idea is like you do several volleys of your search. First, initial kind of exploration volley, and then later you kind of drill down and get kind of eke out the more performance, right? And that's, again, yeah, that's also like semi-automated, right? So like the automated would be if everything is done by one big parameter sweep. The semi-automated means like, well, do several rounds of those large sweeps and inspect the results of each of those sweeps, right? So look at like that sort of multi-resolution idea. Like you have to do kind of human analysis of all those different hyperparameter configurations after that first round, and then plan your next round according to the results of that first round. Next point, so there are better ways of doing things than grid search, right? So basically what I drew there is a kind of grid search, maybe like a multi-resolution version of a grid search, but maybe you should try just doing kind of random values. So there's this paper where they do kind of random evaluations over these parameters. And it turns out, like, for a little bit more complex reasons, that this is often preferred. It's preferred to grid. I mean, it's not that much more complicated. Like the real reason it's working better is because I'm able to see new values that were never appearing on my grid, where it's very sensitive to and where it does very well, right? Versus on my grid, it never really saw that peak, right? So sometimes it can be more helpful to do this kind of random search. And then, or Bayesian optimization is kind of next level up instead of random search. Is like, if you notice that it has this sort of shape, then why would you even bother doing it there? So like, you might begin to start realizing that your kind of likelihoods have certain kind of shapes after doing a few of these random ones, and then using that to guide your next proposals. So that's the basic idea of Bayesian optimization. And cheap validation alternatives. So this is a very nice trick. It's like, if training your full model is really, really complicated and takes a long time, you might not want to train it that many times just to do hyperparameter tuning, right? What you might do instead is kind of train it for a long time using one of the configurations of hyperparameters, and then kind of fix all the weights at maybe like the lower level weights, just fix them, and then only retrain the other, like the top part of your network using the new hyperparameters, right? So this lets you experiment with new hyperparameters much faster because you're not changing the whole model. But then the changes in performance, depending on those, like kind of adapting those top level hyperparameters or the top level weights, like it's good enough for figuring out the hyperparameters. And once you figure out a good configuration of hyperparameters, then you update everything again, right? So anything you can figure out to speed up your hyperparameter search is pretty valuable. Okay, this is like one of the Bayesian optimization papers. I like this because it's like semi-automated kind of flavor, but entirely done by a computer. So what it's doing, so these are like loss curves. As I train my model, my loss is going down, right? But what they do is each of these is a different configuration of the hyperparameters. And then what it's able to say, like, okay, this one is decreasing, but it's not decreasing fast enough. So just save the model where it is, but don't bother training it more. It's wasting computation. It doesn't seem that promising anyways. So instead, go to this other model, which seems pretty good, and like spend more iterations optimizing that one until it seems like, okay, maybe it's leveling out. Maybe I shouldn't be spending so much computation on that one. And then look kind of at a different promising one, right? And then the idea is like, this is a way of kind of, it doesn't throw away these intermediate models. It's able to return to them if it thinks like, at one point I thought it wasn't so great, but now it seems like it's my best bet. I'm going to go back and try to optimize it some more. And it's almost like what a human would do, but they have an algorithm that figures out when to do introduce a new model or optimize one of the previous ones. So yeah, it's this reference. Okay, kind of another intuition that I think it's, like, I had never heard of this until I started working a little bit in deep learning, is that people very often first check to see that their their training loss goes down to 0. So even if the validation loss is pretty high, you first want to see whether your model class is large enough in the first place. Like the kind of intuition is that you want a model class with high variance but low bias, and make sure that you can get the low bias first. And once you have low bias, then you can figure out reducing the variance, right? So kind of the diagram is you want to make sure first that your training loss is going down to 0, because that means you've implemented the right thing and that you have the right kind of general class, function class in mind, and then you regularize that function class so that the validation error also goes down. So that's like a very common intuition. Exercise that you can think about this later, but the point is each of these hyperparameters usually come with some sort of bias variance trade-off, right? So like, kind of, I'll give you an answer for the first one. The wider the layer, that's like the more logistic regressions you're mixing with each other, so it's like a larger capacity model, so it's lower bias, but since there are more parameters and it's a larger capacity model, it's going to be higher variance as well. So you need to be able to, each of these hyperparameters, you know how pushing them one direction is going to change the bias versus variance, and then you can plug that in later, right? So like if you notice that your model now has low bias, you can figure out tuning things towards lower variance. But then if you find like, oh, it's not training down to 0, I need less bias, then you know which knobs to turn to make it lower bias. So it's just guiding that search a little bit. And then finally, besides these hyperparameters, kind of, it's useful to look at things besides just, like I know that TensorFlow or PyTorch or whatever you use will, like the most easy thing to plot is the loss curve, right? Or the validation loss and the training loss, but don't just do that, right? Because it loses too much information that might be useful down the road, right? So the kinds of things that are useful to keep track of the gradient values, right? So this is these are both papers from, I think it might have been just before the ImageNet paper, and like people were actually understanding a lot of the details of how training is working, and this is how they used to propose. Also, like Relu was a similar kind of experiment where they keep track of all the gradient values. So what they're noticing here is like, oh, the gradient on the highest layer is very, very small for a long time, but then eventually it starts growing, right? And then they had to come up with different different changes to activation and architecture, which have that final kind of semantic layer start updating a little bit earlier. But if you had not kept track of the gradients, you wouldn't have even realized it. And you might have started thinking like, oh, maybe this last layer I can start interpreting, when in reality it hasn't even been updated, right? So you need to, like, those sort of statistics are useful. Kind of another very neat idea. So it's, okay. Looking at the parameters of a deep learning model is not that useful, right? Because, you know, you can think of switching, you can do all sorts of like permutations of parameters and get the same function at the end, right? So it's not like just analyzing, like besides thinking about whether they're 0 or not, there's not much you can say, right? But an idea that this paper had was, well, let's ignore the parameters and think only about the overall functions, right? So before I was drawing all these kind of like complicated mixture of logistic things, what they're doing is they take a pair of like x and y values, right? They concatenate these into long vectors, where basically, yeah, so like, okay, let me, from the beginning, what you do is, I have a whole bunch of images, say. These are my training xi's. I have one deep learning model, I have another deep learning model, right? This is one deep learning model, here's another deep learning model. What I do is I pass in that image, and then I pass it through my full neural network until I get like k logits for my different class probabilities, say, right? So it's like probability of being a car, probability of it being an airplane, and then you have these k numbers. And I get that for one image, and then I get that for another image, and I do that for all the images in my training data set, right? So this is some big matrix of logits, right? And now the thing here is that since I'm learning the function directly, like all these kind of permutations I could have done on the parameters, it doesn't matter because I'm ignoring the parameters entirely. I'm only looking at how the parameters affect my prediction, right? And the point is, I have this new big matrix of y values. I can collect that at every stage of training, right? So I can see how does my kind of vector of logits evolve over time. The issue is this is a very large dimensional object, right? So you can't just plot the k by like however many training examples matrix of logits, but you can do dimensionality reduction, right? So what they do is they take each of these dots is one training. It's like they do the dimensionality reduction of that big matrix of logits at that one time point. And then they look at the sequence of time points and how that function is changing, right? And then the color is the number of iterations, right? So kind of a beautiful thing, I think, in this paper is that these are two models that get similar performance in the end, but then they don't land in the same place, right? Like this one starts here, it lands around kind of this big kind of range. This one starts here, lands out here. They both get similar performance, but the functions that they've learned are very different, right? And the reason you know the functions are different is that they're landing in different parts of the space. It's irrespective of the parameters, right? The actual shapes of the functions that it learns are different. So I think that's a very neat idea. I don't see people do this very much anymore, but it's something that I think people should do more. Okay, and last slide for this section. So my first point, just what I said now, right? Don't ignore the history, right? It can feel overwhelming when you see so many tweets, and I don't even know what you young people are using these days to keep track of deep learning models, right? You don't need to learn everything. Like I mentioned this yesterday to some people who talked to me about, there's a book called Parallel Distributed Processing. It's like Jeff Hinton and McClelland. These are like people who created deep learning in the 80s. And like that book, I think, has a lot of very deep ideas that are totally lost now. But I think if people start paying attention to that, you might find much more creative and interesting like theory and applications than just rehashing something that people just came up with. That's kind of one general point for anything you learn, really. The second is when you see these new algorithms, right? If it seems like bewildering notation, and if it seems like totally inaccessible mathematically, it's probably because it's written poorly, right? There was a point where I thought, oh, it's because I don't know enough. But now I realize, no, like good writers can explain things clearly, right? And the way that they do it, I began to realize, is like they had a lot of examples. They had a lot of like plug-in numbers into the formula, right? Like plug in infinity or negative infinity into your sigmoid function, so you see just what it looks like, right? This makes things a lot less mysterious. I think if this were a requirement for like ICML or iClear or anything, like the papers would become much more readable. So yeah, that's one. And then finally, don't believe anyone who calls himself a programming genius or like a deep learning genius. This does not exist. Like they're musical geniuses, they're mathematical geniuses, but then even then, like you need to practice, right? One of my favorite quotes is, "I'm not a programming expert, I'm a Stack Overflow expert." This is very true for how you actually develop things. And kind of my final, while I'm like harping on this, you can't learn everything overnight, right? Like as many times you see online, like learn deep learning in 6 weeks, or like one weird trick to learn deep learning. It's like, no, don't believe any of this. It takes time, but I think it's worthwhile in the end. So yeah, that's all this.